comes to liquid mixtures, thermodynamics of liquid mixtures, there's two things kind of happening at once, and it gets me kind of confused, which again, that may be why memorization is a good strategy on this. And that is that we've got these chemical potentials of A and B, and of course I have to have A and B. I've got to have two things to have a mix. And these are their chemical potentials changing. Before I get into that, let me just remind you that in an ideal case, that delta G, and I don't know if there's a little circle there or not, let's put it there, is defined by these excess functions. And again, this is, you can say this for any process, right? And for ideal, this is 0. Remember of your little proof, the little proof I did, which was that there's no volume change and there's no internal energy change, so there's no H change. And we also derived, let me do this per mole, sorry about that, let me do this per mole so that everything's a chemical potential. And this ends up being RT, Ka-ln Ka, plus Ki-B ln Ki-B. Okay, so we've got this. It says that everything mixes because this is automatically negative unless one of the Ka-A's is 0, in which case you don't have a solution to begin with. So what are we doing? So again, this is always this is the delta G. This is always negative. All right, so there's this aspect of liquid mixtures. It says all ideal solutions mix. Okay, then we go back to here, and then we get the nitty-gritty details about the chemical potentials of the A and B. And so remember that. All right, so the one reason I wrote this, I didn't do this last time. I'm actually reviewing, but I did put this last time. I don't think I put this up here. It's not in my notes, and I think I forgot to do this. I should have put this up here, and this is to remind you that this is perfectly true, right? So remember, I mentioned that a lot of what we're doing from now on are nothing but approximations. And when I got to this point, I did say this in class, but it bears repeating, that when I got here, everything's fine, and everything from here on out is not. It is true that chemical potential of a pure substance at its, if its vapor pressure is the pure partial pressure of that same thing, then this is 1, and ln1 is 0, and therefore the pure chemical potential is the pure chemical potential. All right, that's brainless. All right, but what happens is when you dilute, you start making approximations, and here is Reynolds' law, where you say, here I need it on the side. And remember, Reynolds' law is just about completely wrong, and it just says that the partial pressure is equal to the mole fraction in the solvent times the pure partial pressure. And again, that really makes a lot of sense to me. I would think that this would be a very good approximation. Instead, it's a terrible approximation. It always surprised me, but whatever, what do I know? Great for toluene and benzene and ethanol and methanol. It is not good for water and ethanol. And just about anything you'd ever care about, this does not work. Regardless if we use it, this is child's play. Okay, knowing that this doesn't work, we then go to the ideal dilute solution. Now, remember that I tried to call B the solvent. So the solvent will still follow Reynolds' law, and I'll draw some graphs to remind you that. And the wackiness gets in Henry's law. And here, let me actually draw the pressure versus mole fraction graph, which I drew last time. I usually do this in terms of B. And this would be the Reynolds' law, a straight line, because this is the formula of a straight line. And what actually happens, because that's ideal and nothing is truly ideal, that for the most part it actually looks like this. And what the Henry's law is just a redefinition of the pure partial pressure. And so, yeah, there you go. You just, right, it's kind of simple, but what I just don't like about it is that it's just a very absurd thing to say that this formula doesn't work. This formula doesn't work anymore when I try to come up with something new to put in here. All right, so this is fine, this is 100% correct, but when I try to put the mole fraction in here for a solvent, when I try to get this in terms of a mole fraction, it just doesn't work. So I come up with a number that makes it work. That's what this is saying. Look, I did post the extra hour on Friday. There's applicability of Henry's law with gases and liquid sets on the extra hour. It has been posted. Sorry, I was late. But anyway, yeah, there you go. So that's really the big picture. And what I got into last time, actually, I really was kind of flubbing. I know I was very tired last Friday. I finally finished up my grants. I kind of felt you guys were really in outer space myself. Not to blame you, but I think between us both, I felt like I was just babbling there towards the end. Almost fell asleep standing up like a, what does that, camel? I forgot what animal does that. But, yeah, horses do that. Actually, if a horse lies down, I used to ride horses. If a horse lies down, it's sick, so you should shoot it. No, only shoot your own horse. That'll get you in trouble. Okay, so what I was talking about last time, and I know I was just really kind of out in outer space, was that this is the ultimate BS, and at the same time it's not. For one, okay, can I describe this a little bit better? And number two, what about these nether regions? All right, now this is where the idea of activity comes up. And what I really screwed up last time was I didn't start out defining activity better, so I wrote some extra notes. Okay, now remember that if I insert this thing, and I'll stick with the solute, remember A will be my solute. Depends on the mole fraction, but let's just call it that for the heck of it. Okay, if I insert this into the chemical potential, it's perfect. All right, now remember, this is test 1, test 2 material. Okay, so this is fine. If I insert it into there, everything's fine. So I call that the activity of A. So nothing is wrong. This is where activity is really a strange thing. Right now, activity is perfect. Inserting activity into here is perfectly correct. Now, here's where it gets funky. Now, I said already that trying to shove in the liquid's mole fraction just doesn't seem to work. It doesn't work, so let's just multiply by a correction factor. Okay, so this was what bothers me. Okay, this form of activity is perfectly fine. There's nothing wrong with this. I probably would need to make a lot of measurements, but it's not like I can't do that. But then this form of activity is complete BS. This is the equation didn't work, so I just came up with a number that made it work. It's both at the same time, so I find this very strange, and I've never really understood it better than that. However, what I do have is I have an out. Okay, so again, this is activity. And what do I want to do with this? Okay, as much as this in this form is all BS-y, it does have a saving grace, and that does allow me to understand why solutions are neither ideal nor ideal dilute. And that is in the idea of excess enthalpy. So I'm doing kind of a new derivation. I'm not going in a different direction, although I am still reviewing. I said last time that I had an idea of a phenomenological model, which is that there's a mixing enthalpy. So again, remember up there, that's ideal solutions. Ideal solutions have no mixing enthalpy. And now I'm saying, well, what if it does? Oh, my symbology is wrong. And again, if you forget, because I just forgot the per mole, I'm going to do everything per mole. Just, if I screw that up, don't worry. And this would be, remember I said that there will be a factor that determines whether something gets hot or cold and how much, and that's beta. These two Ki's are clever in case you don't actually have a solution. One of them would be 0, so there'd be no mixing enthalpy. And then I'd have an RT. Per mole, there would be an N there. That's what I said last time, but I'm just going to move it up this time for the heck of it. Okay, so now what do I want to do? I want to point out that then the delta G mix, so therefore, now here's what I'm going to want you to do. I want you to look at that, keep that in mind, which is the ideal, and then this will be, let me do per mole. This will be in contrast to that. But then what I'm going to do is I'm going to equate them. So what I've got is something that looks like this is the T delta S part, by the way, the minus T delta S part, chi A, L, and chi A. That's chi B. ln chi v. Okay, so this is minus T delta S. And then let me insert the enthalpy part. Okay. So that's the enthalpy part. All right, now what I want to do is also equate this to this idea of activity. So if, I should have done it this way. My bad, I wasn't planning ahead. I should point out that the idea of activity does this. It turns that equation up there into this. Bracket chi A ln activity. Remember, this makes it perfect, plus chi v. Remember that these chi A's and chi B's just come from the fact that you need to include you need to know the moles of A and B relative to each other. How could you not, right? In case you don't have a solution, one of them is 0. So, okay, so again, big summary one more time. All of this stuff up here is BS. Try to remember it, because I'm sure I can ask a true and false question. Reality is, you really got no good substitute for this, and if you try, you're going to have this crazy BSE factor that just you would certainly make it work, and that gives you the equation for delta G. Question B, right?
Yeah.
Thank you. I have to edit the video. Yeah, that's when I just start rambling. Okay, so again, this is just forced to work. Now, the neat thing here is that I've got what apparently is a different equation where I've included enthalpy. So again, forced to work, of course it has to work because I have this BSE correction factor that I will set to whatever I have to make it work. And then I've got this thing, which is a phenomenological model that says, gee, you can't forget that things get hot or cold when they're mixed. Okay, so I'm going to do something really wacky right now, and so you're going to want a whole page. I'm going to show that these are the same thing. Now, the reason that I want to do that is because, again, as much as I hate this because it's just made up, I can equate this to this. In other words, the reason I have to have these wacky factors that are forced, that I have to use to force it to work, comes from excess enthalpy. This I don't believe, but this I do. Right now, I know that things get hot or cold when mixed. And sometimes they don't at all, right? But that's kind of, again, the point is that's kind of rare. I know that things get hot or cold or mixed, and therefore I'm going to understand activity, and that is activity, state, and grace, especially this weird correction factor. All right, now to do that, this is going to be a Carnot type thing. I'm going to do a derivation, and it's quite long. And so you want to leave a lot of space. What I'm going to do is I'm going to start from the top, deriving one equation, and I'm going to start at the bottom from the other and work that, and I'm going to meet them in the middle. Okay, that's probably confusing right now. Here, let me just go ahead and start writing stuff down. And you just follow along, because this is kind of wacky how this works. All right, at the top, I've got delta mix G per mole, RT, and I'm just writing the same thing again, chi A ln activity of A plus chi B ln activity. Can we do something? You're good. Okay. Cell phone, huh? All right, anyway, writing a test just for you. There we go. All right, now what else can I do? I can insert the, again, I shouldn't say this on the camera, but I can insert this BSE form of this definition of activity in terms of mole fraction. So I'm going to write the mole fraction here. So it looks like I'm writing down the Rayu's law form, putting chi A ln chi A and chi B ln chi V. Okay, so what happened was that wacky gamma factor is now here. That gamma factor that I just make things work with. But remember that this is going to give me, this is going to allow me to equate this to the enthalpy. Sorry, so this doesn't get confusing. And in case you get a little bit lost with what the heck just happened, ln A times B is ln A plus ln B. And of course I'll have these identities if you need them on the cheat sheet on the test. So anyway, that's just what I did here. In case it's a little bit confusing, just want to remind you that this is what I did. Just inserted this and I used this identity. Okay, now this is where I'm going to get a little wacky. 1, 2. Okay, so that was fairly simple. Reminds you what I'm doing. Okay, I'm going to start with this enthalpy form. Okay, am I doing this right? Yeah, I'm doing this right. Okay, RT, Chi-A, ln Chi-A. So remember, this is minus T delta S. And this is not an ideal or ideal dilute solution because there would be no enthalpy. Beta Chi-A, beta Chi-B. Sorry, I don't need a parenthesis there. I'm just using parentheses. Okay. Okay, the next step on this guy is, you see, I'm going to work up. So this guy makes, I mean, this is, again, 8th grade math. I'm going to work up from here. The next step is really subtle. So same deal. And you see my point is, you see how I'm going with this? You see that this already matches that. This matches that. All I have to do is get this to match that. And now I can equate activity to enthalpy. That's the goal. That's the executive summary. Okay, so there's not much to do with these Chi-A's and Chi-B's, so I'm just going to write those down again. So I know what's your risk. Wait till we do the final review. You're going to be in awful pain. Okay, now this is where it gets a little funky. So I'm just writing this down, and normally I'd have to stop. But what I'm going to do is I'm going to multiply this by the number 1. Okay, sorry. I'm going to multiply this by the number 1. Sorry, I'm just kind of going in a weird order. Little bracket. Okay, notice that I've multiplied by the number 1. In case you get lost in your own reviews, equal to 1. Okay, 1.0. All right, in case you're having any trouble seeing that. Right, 2 things, the mole fractions add up to 1. Okay, why did I do that? Okay, so now I'm meeting in the middle. And I'm still going from the bottom. And I see that these equations right now, they certainly look identical. Okay, now I've got these two terms that do not seem identical. Let's see. Okay, I've got a Chi-A here, so I'll write that. And now I've got a bunch of other stuff. I got a beta, and I got a Chi-B squared. Okay, next term. I've got a Chi-B. And let's see, what else have I got? I've got, I've already done this term, so I've got a Chi-A, I got a beta Chi-A squared. Okay, I'm done. Yeah, kind of painful, right? Kind of like Carnot. Maybe not quite as bad. Okay, now here's the end point. Remember, these gammas are the BSy things. Sorry, I'm kind of messing this up right now. These gammas are the BSy things, but now I see where they come from. So let me write that down. Therefore, therefore gamma A. Remember, this is the correction factor that I said was just made up, but now it looks like it's not so much Chi-B. There we go. Okay, so there you go. I know this is just a bunch of spaghetti right now, but again, the big picture is that with this inclusion of enthalpy, which I know is there, a little bit of a model, which makes a lot of sense, not because it's perfect, I can then derive these correction factors that define activity, which before, again, it was just something I made up to make it work, but now I see why I had to make it up. I even see where I had to get it from. it's defined by the enthalpy, specifically whether you're hot or cold and how much. And so that makes a lot of sense. All right, I can even do more with this. And so what I'm going to do now, and I told you this is really going to hurt your wrist, I'm going to do basically that chart I made that I just erased, I'm going to redo it again with this information. And then this will hopefully put all of Henry's law and Reynolds' law together, and then we're just going to drop it. Now, of course, I would not expect you to do this derivation. Just like Carnot's cycle, did I ask you to do Carnot's cycle to draw the whole thing on a test? Of course not, or to calculate the efficiency. Made good, true, and false questions, right? Question up there?
Yeah, my point was the gamma A equals beta chi b squared.
Yeah.
Is it supposed to be ln gamma A?
Oh, ln gamma, ln, right. Yeah, thank you. I'm going to have to do a lot of video editing. Oh, I don't even think I can fix that. Right, ln, my bad, yeah. Because it's actually exponential. Yeah, thank you. And then ln chi b here. Sorry, yeah, folks got to catch me. Come on, that was obvious. It's like Friday over again. I don't even know what was wrong with me. I was just very tired that day, too. Notice that one thing that's kind of neat about this is, that the correction factor of A is determined by the mole fraction of B. Reality is what I can do is I can just make that 1 minus chi A squared, and it makes a bit more sense. But anyway, I'm actually spoiling a little bit. Thank you for correcting that. That's a gigantic mistake, by the way, as you're going to see here in a second. Okay, now, as painful as this is, let's remake that table I started out the lecture with and do it over again now with excess enthalpy as part of it. And again, the point of this is that I hope that this gets all of this across at once. And so again, I will define A as the solute and B as the solvent. Now remember that depends on mole fraction. It's just I have to call something something. And here's where I just about screwed up. And again, I will recast. I'll get all the A's on the left and all the B's on the right. Why do I keep doing that anyway? Gamma B, beta. That's just not thinking ahead of myself. I shouldn't do that anyway. Okay, so that's the thing we just derived. Now what I can do is I can say gamma A is e to the beta. Okay, what I'm going to go ahead and do is I'm going to go ahead and insert that chi B, the mole fraction of B, is actually 1 minus the mole fraction of A, because I don't like having A's and B's mixed up here. It's just unsatisfying. I want to think about the solvent and the solute depending on each other. Okay, so here's the correction factor for the solvent. E to the beta 1 minus chi B squared. Did I do that right? Miracle enough. Okay, now I can define the activity. Activities, again, are the gamma A, chi A. So I've already defined that, so that's chi A, e to the beta. I'm just writing all this over again. And remember, I'm kind of painting myself in a corner here. Don't forget that this is perfect, right? And then over here, in case it gets a little confused in your notes, let me just do that. Okay, so this is the activity of B. Sorry, I'm in the way. This is the correction factor of B times the mole fraction of B. Now I've got a good theoretical description of the mole fraction of the gamma factor. Okay, there you go. And then last bit is that therefore the partial pressure of A is equal to chi A. So this is the part that I'm going to make it clear the differences between Henry's and Reynolds' law. Chi A e to the beta. I'm just kind of writing all this over again. Okay, and then the same for B. Because everything seems to come down to what the partial pressure is. And then I'm going to show you where Rayleigh's law and Henry's law comes from. And this is the stopping point, so you might want to just underline this right here. And remember, once we would know what the pure, if I'm mixing water and ethanol, I'm allowed to know what the pure partial pressures are because you can just Google it. For any specific solution at some exact stoichiometry, maybe you can find a number in a table in an encyclopedia in an engineering library for a solution concentration that's close enough or the same. Regardless, what you can do is calculate the new partial pressures from this guy here, and once you have that, then you know exactly what the new chemical potentials are, and you can figure out whether things mix. And yeah, there you go. All right, now, again, I said that I would be able to derive Henry's law and Rayleigh's law from here, and I can't. So let me do that. Let's see. Now, this is the solute. Okay, so the first thing I want to see is I want to see if I can find, let's see, what do I want to do? I want to see if I can find Henry's law. And Henry's law is only for when A or B is a pure solvent or solute. Remember that Henry's law is for the ideal dilute solution. So that means that I've got to dilute something. And by dilution, it means that chi A would be close to 0. And therefore, the partial pressure of A is just chi A e to the beta pure partial pressure of, whatever you look up on Wikipedia, the pure partial pressure of water. As I mentioned to you, if you're at 0 degrees, it's 600 pascals for water, which is something I remember. And now I see where Henry's law comes from. You see, that's the Henry's law constant right there, right? So again, remember, I said it was a redefinition. Henry's law is a redefinition of the pure partial pressure. That's where it comes from. It has to be redefined because of the enthalpy. You can imagine that if the solution gets hot, you have higher, I'm just kind of throwing this out. I don't really know if this is true, but just imagine that the thing gets hot, then maybe that makes the pure partial pressure higher than it should be, right? So that's the idea. Okay, if beta goes to 0, now this means that you're an ideal solution because there's no enthalpy, then what I've got is the partial pressure of A is chi A, let's see, e to the 0 is, okay, chi A pure partial pressure of A. And that's Rayleigh's law. Right? So if there's no excess enthalpy, then I'm not in an ideal dilute solution, I'm in a pure ideal solution, toluene, benzene, methanol, ethanol. Okay, and that means that the solution wouldn't get hot or cold at all, and there you go. You get an ideal solution. Question?
So that means that the solution is pure then?
Is what?
That means solution is just pure.
It would be like methanol and ethanol, where they are so trivially similar that I don't even know why you'd mix them to begin with. Right. So remember, water and ethanol do not even fit into this, and we're actually going to even go into more of that. So again, big picture here, that for the solute, I can describe all of Henry's and Rayleigh's law with this excess enthalpy, including not having an excess enthalpy, which gives me Rayleigh's law. Anyway, okay, let's do the same for B. Sorry, I'll toss this up here in a second. Okay, now, ideal or ideal dilute both have solvents being solvents, right? So for a solvent, chi B must go to 1, in which case the partial pressure of B is chi B e to the 0, which is 1, PB star. Okay, it's Rayleigh's law. So ideal dilute solutions, the solvent is, so remember before, when I was applying this stipulation for ideal dilute solutions, I got Henry's law over here, but I get Rayleigh's law over here. I should have, right, because this is the solvent. Okay, now, if beta goes to 0, therefore PB is chi B, same thing. There you go. Let me toss this up here. So, all right, they're not cooperating. Put them against the wall. Oh, I hate these boards. Actually, they're kind of nice. Well, yeah, maybe you on the front row can't quite see that, but hopefully you have it. Sorry for the density of the letters up there. I should have spaced it out a little bit more, but that's the best I could do. And so, yeah, I think is that all I got on this? Yeah, and so, yeah, now we're ready to move on, actually. So when it comes to, actually, you know what, let me go ahead and just take one slight turn and let me tell you about a question that I'll have on the test. Again, I'm starting to write the test now, way ahead of time, but whatever. And so I thought of a question the other day, and it may, I'm hopefully not complicating things more because I know that this is a giant bloody mess. This is like Carnot, where I'm writing across the board, and I know that's a little bit a lot to take. But I do want to show you something because it's on the next homework, and I did write a question like this on the test, which is to show the relevance of this, of all of this, like chemical potential, this and that, which is something I've never found in a standardized test before. Something I figured out on my own, but I'm surprised that I'm right because I'm just surprised. And it's actually kind of interesting because it makes this stuff actually worth something, so it's not so abstract. And what I found was, let's see, again, knowing that, let's not worry about whether it's A or B. Okay, so RTLN, partial pressure over the pure partial pressure. So I'm not trying to stipulate whether you're A or B or anything, just because I don't want to. Okay, so I was looking at this, and as much as this seems like kind of like whatever, I actually found it has a really neat use. Now, again, so that this isn't so abstract, so that you can plug it up there, so that you can plug in numbers that you can get in the table in the back of the book and see that this actually means something that's measurable. I want to point out to you, and again, you have this on the homework question, and next homework, obviously, and on the test. What I did was I looked up the formation G per mole. Remember, that makes it a chemical potential of water. So all this is H2O. And this is the liquid. I should put a little L there, but anyway, minus 237.1 kilojoule. It better be per mole because it's a chemical potential. Okay, and then I looked up the same of the, is that the liquid? Yeah, the gas. Okay, so water vapor, and it should be less, right? Yeah. No, it should be higher. Higher, of course it's higher. Kilojoules per mole. Okay. So here's what I figured out. It turns out I'm actually just perfectly right about this. And especially this is a good, what we're going to do on, on Friday, we're going to get into phase diagrams. So this is like a good introduction to that. I want to point out that these are chemical potentials. And so I was looking at this and I thought, okay, for two things in equilibrium, they have to have the same chemical potential. But then that also doesn't make sense. Let's talk about water. Okay, water at STP. Would the chemical potential of the liquid or the gas be lower? Now remember, at STP, water is predominantly in the liquid form. What has the lowest chemical potential? The thing you see or the thing you don't? Right, the thing you see. Right, remember when we did ice melting. Ice melts because the chemical potential of the solid is too high. Remember, that's because it's hot. The chemical potential of liquid water is lower. The chemical potential of solid water is higher. The solid melts, okay? Now, in the case of a bucket of water at room temperature, you know that for the most part it contains itself as a bucket of water. Look at that, it's a lower number. Don't, you know, I know they're negative, that's kind of a pain, but this is a lower, bigger negative number than that. Therefore, liquid water likes to be a liquid. Okay, but I know that they still have equilibrium, right? So I should be able to equate these two. And the way you do this is, again, just using this formula, which I tried to make generic, the liquid would have to be equal to that of the gas. The reason, though, that they're not, remember, these are the chemical potentials, they're not the same. Why aren't they the same? Is because you've got to take into account the fact that they would be equal if the partial pressures were the same, right? That would be equilibrium. So what you have to do is this. You have to figure out, let me actually spell this out, vapor pressure, which you can look up in a book, vapor pressure over 1 bar. Okay. So basically what I've done here is I've said that the liquid has to be equal to the chemical potential of the vapor. But remember that the vapor has to have the right partial pressure. Right? So again, this can be a bit of a headache. Again, chemical potentials of liquids and gases and the vapors that come from them, they have to be equal or they're not at equilibrium. Right? But now I look at this numbers and I'm like, well, but they're not the same. Right? Well, that's because liquid doesn't just suddenly boil off into the gas phase at room temperature. But at the same time, I know that they have to be equal. So I'm like trying to confuse. The solution is to remember that the number in they're in equilibrium, but the chemical potential of the gas has to be changed to account for the fact that it doesn't have 1 bar of pressure. So let me say that again. The liquid and the vapor have the same chemical potential, but I got to remember that my chemical potential in the table in the back of the book is not right, because this is done at 1 bar. The liquid and the vapor are in equilibrium at the vapor pressure, not 1 bar. So therefore, I have to take this number, which is true at 1 bar, and I have to adjust it by what the actual measured vapor pressure is, and then they truly are equal, right? So this is the chemical potential of the vapor, at the right vapor pressure. Okay, now here's what you can do. And this is the question on the homework and on the test. If you get the numbers in the table in the back of the book, remember that your reference pressure is 1 bar. You can calculate the vapor pressure of liquids, right, at 298. And when I did that, for using these numbers, you do it or wait till next homework because you're going to do it then, you actually get the correct vapor pressure of water. Again, using these numbers in the table in the back of the book, you solve for vapor pressure, and you get dead on to like 5 significant figures. What I Googled, the correct vapor pressure is of water at 298.15. Actually, here's another trick. Remember how I told you that, remember I was asking you, where the heck did they get this number? How did they measure this when you can't make water have 1 bar of pressure at STP? It would rain, right? If I had a container with vaporous water at 1 bar at STP, it would suddenly turn into a liquid. I can't make the measurement. That's actually, this equation, that's actually where they get the number from. Right, so they make the measurement at the pressure that they can, and then they extrapolate it using this guide to 1 bar, and that's where this number actually comes from. They never actually directly measured it. So, yeah, with that,